My name is Michal Leskes. I'm an associate professor at the Weizmann Institute of Science in Rehovot in Israel. So we work with magnetic resonance, and the research questions that we are trying to answer are in the field of material science. Specifically, we are interested in understanding how battery materials work. We are looking at how ions are moving within the battery cell and how the chemistry of the battery cell is affecting the motion of ions. And for that, we need to be able to detect these ions and detect the chemistry within a battery cell. So for that, we use a solid-state NMR spectroscopy. And we need to be able to, and a lot of the chemistries that we are trying to detect have very low quantity inside a battery cell, so we also have to somehow enhance the sensitivity of solid-state NMR spectroscopy, and we do it with an approach called Dynamic Nuclear Polarization. The main approaches in magnetic resonance that we are using are solid-state NMR spectroscopy, and we increase the sensitivity using dynamic nuclear polarization in the solid state. And basically what we are looking at in a battery cell are thin surface layers that are very disordered. So they are very difficult to detect with other approaches such as X-ray crystallography. You may do some other spectroscopies, but the chemical ability to distinguish different species is very limited compared to NMR spectroscopy. So with the NMR spectroscopy, we are really able to detect these thin surface layers within a battery cell, and we are able to say what exactly is formed when the battery is working. And we use DNP in order to increase the sensitivity so that we can detect these species with a very high quality of spectra. What we are working on at the moment is one approach is we can use the standard approach that you can use dynamic nuclear polarization in solid state. For example, you can for DNP, for dynamic nuclear polarization, you have to have unpaired electrons in your samples. And typically you add them to the sample. But because the battery chemistry is very sensitive, we are always concerned that this might change what we observe. So we are developing ways that we can detect our systems with spies from within it. So we can have introduce electrons that are part of the structure of the electrodes, for example, in the battery itself that we are studying. Or we can use electrons, conduction electrons, like in lithium metal, to increase the sensitivity. So we are trying to develop approaches that allow us to probe the system without interfering too much with the system itself. So the biggest challenge that we have in energy storage is how to be able to make these materials safer, cheaper, and lasting longer time. So these are three very big challenges, and each of them requires completely different approaches in material science as well as characterization. In material science, typically the way you approach it is that you have some idea and you try it, you replace a certain component inside your battery cell and you see how it works. But it's very hard to get mechanistic understanding as to how a specific change caused a specific result. So we use NMR in order to rationalize these changes and really understand the mechanism of how one material acts versus another material. And I think that's quite unique insight that NMR is giving us. So in the past few years, I think there are two main achievements that I'm very proud of and very happy to share. So one is that we can use DNP in solid-state NMR to increase the sensitivity and detect few atomic layers formed on an electrode material, which is very nice from the magnetic resonance side, but also practically very important. And the other aspect is that we found ways using NMR. Actually, we are adapting methods that are used in NMR to study proteins, and we adapt them to study mobility in batteries. So completely different systems, but exactly the same magnetic resonance tool that allows us to see how ions are moving between phases in a battery cell. So these two things. So the benefit to society, I think, is that we are able to now say how specific changes, if you introduce a different chemistry into a battery cell, how is that improving it or deteriorating it? Often it also deteriorates it, but that's also information that is useful for us to move to the next step. So like I said, we are trying to make the process of designing better materials more rational, not just based on trial and error, but actually trying to understand, and from that, I believe that we can develop better materials. My research group works in two directions. One aspect, we are developing new approaches in magnetic resonance, and the other aspect is to apply these methods to understand battery chemistry. But These approaches are not limited to battery chemistries, and they can be applied to a wide range of materials, solar cells, catalysis. So I would like to see how these approaches are used in more and more different kind of real-life problems.